We're going to tackle relay setting calculation for medium voltage motor feeder relays. This will be our single line diagram to where our MB motor is connected. This will be our multifunction relay. It is composed of protection relays at the same time with metering. And this will be our line CT. Okay, the ratio is 150 is to 1 ampere. And this will be our zero sequence current transformer. Okay, the ratio is 25 is to 1 ampere. And our subject motor here. Okay, and this will be our protective device. Okay, it's a combination of fuse. Okay, and 200 ampere fuse and a 630 ampere contactor. Okay. Okay, so we have now in our data sheet of our motor. Okay. By the way, our point of discussion right now, we will going to use the relay from GE, which is the model number is M60. This is motor management feeder relay. Okay, our CT ratio is 150 is to 1 ampere. Okay, the Varden is 10 VA class 5P20. Our zero current transformer is rated 25 is to 1 ampere. And our voltage transformer is 11,000 or 11 kV is to 110 volts. Okay. Our rated current of the cable, our proposed cable from here will be equal to or greater than 101 ampere. And our 11 kV minimum line to line fault on this motor side will be 9,103 ampere. And our line to ground fault is 409 ampere. Okay, these two values here, the minimum line to ground fault and the minimum line to ground fault, is being taken by actual power system study. To be specific, short circuit study, minimum short circuit study. Okay, and our line capacitive current is equal to or less than 1 ampere. Motor is induction motor or asynchronous. Okay, and its rated voltage is 11 kV with rated current 101 ampere. The no load current is 26 ampere and the power of the motor is 1,650 kilowatt. Okay, at 100% of load, the efficiency is 96.5%. And also the power factor at 100% of load is 0.89. Okay, its rated speed at full load is 2,986 RPM. Okay, and the starting type is direct online or DOL. Okay, our starting current is 5.8 times the line current. Okay, and our maximum stalling time when it is warm, okay, is 13 seconds. Okay, next, our allowable running up time. Okay, when the terminal voltage of the motor is equal to the nominal voltage, okay, the allowable running up time will be 9.4 seconds. While if the terminal voltage is equal to 0.85 of the nominal voltage, our allowable run-up time will be 19.5 seconds. Okay. For the starting time, okay, at rated voltage, okay, when the terminal voltage is equal to the nominal voltage, our starting time will be 3.6 seconds. But whereas if our terminal voltage is equal to 0.85 of the nominal voltage, our starting time will be 6.1 seconds. Okay, the heating time constant will be 25 minutes. and the cooling time constant will be 150 minutes. Okay? The number of consecutive starts, okay, when it is cold will be 3, and when it is warm will be 2. And the number of starts, this will be properly spaced in 1 hour, will be 3. Okay? Next, these are the relays, proposed relays for our motor feeder. The first one, we have here relay 48 or the excessive start time protection. Okay? This relay 48 protects the motor from prolonged startup procedures, thus supplementing the overload protection. Okay, so this relay 48, this will be our second line defense on overload protection. Okay, in particular, rotor critical high voltage motors can quickly be heated above their thermal limits when multiple starting attempts occur in a short period of time. If the durations of these starting attempts are lengthened, for example, by excessive voltage surges during motor starting, or by excessive load moments, or by block rotor conditions. Next, Relief 49 or the thermal overload protection. This will be our first line defense for the motor overload protection. Okay? Next, uh, relay 46 or the negative phase sequence protection. Uh, yes, the presence of negative phase sequence currents in the rotor of a motor causes detrimental heating. The cause of the negative phase sequence currents could be an internal or an external malfunction. An internal malfunction, rather, may be a minor or major phase-to-phase fault in the stator windings. An external malfunction could be a depression in one of the incoming phase to neutral or phase-to-phase voltages. The motor will then be fed from an unbalanced source of voltage and will respond by creating unbalanced currents in its stator and rotor conductors. Negative phase sequence relay will be used to protect motor from a harmful overheating. Okay. The next relay will be relay 51LR or stall detection protection. Okay? If the motor fails to run up to full speed during the starting period or is suddenly forced to run at a low or zero speed, then the stator current will be at or near its starting value. This will cause overheating of the stator and rotor conductors, and the much cooling airflow will aggravate the problem. Stalling is determined by checking the current is at or near its stalling value, and the tripping time is between the cold and hot thermal times for this current to protect the motor from this kind of abnormalities. We require to have a stall detection relay or 50 or relay 51 LR for this type of abnormalities. Okay. Next will be relay 27 for phase under voltage protection. Relay 59 for phase over voltage protection. Relay 51 for phase time delay over current protection. Relay 51G for ground time delay over current protection. Relay 66 for the start number protection. Repeated starting of a motor in close succession will cause the accumulation of heat in the conductors and body of the motor. To safeguard against damage, it is desirable to limit the number of starting attempts that are made in a predetermined time period. A well-specified motor will have a prescribed number of starting attempts. For example, 2 to 5. A rest period before the same attempts are repeated. The rest period is typically half an hour to 1 hour. This should apply especially to motors that have long starting periods, such as motors that drive high-speed compressors. Okay, so to ensure that overheating will be avoided due to repeated starting of a motor, start number protection relay is required, or the relay 66. Okay, we have here relay 37 for loss of load protection. Most high voltage motors operate at steady loads between 75% and 90% of their rated power capability. Should the motor suddenly find itself underloaded, then it is possible that the driven machine has inadvertently lost its load. For example, a pump loses liquid at its suction port. This may not present a problem to the motor, but the driven machine could be damaged if it is allowed to operate continuously in this state. To protect this kind of detrimental scenario, start number protection relay must be provided. Okay? Last will be the Sonde temperature in windings. Okay? Resistance temperature detectors, for example, the 100 ohms platinum elements or thermocouples, are usually embedded in 3 stator phase windings to detect overheating in the vicinity of conductors. A set of 3 is normally used, and a second set of 3 is specified as spare detectors. The active elements are wired to threshold relay that gives the first threshold will be an alarm and the second threshold will be tripping when the temperature is exceeded. Okay, so from here, all these relays from here are within this M60 or the feeder motor feeder management relay from GE. Okay? Okay, so let's start our relay setting calculation. Okay, first one for the relay 48 or the excessive start time protection. Okay, our threshold here is set to 200% of the nominal current. Our nominal current is 101 ampere, so multiplied by 2, that's why we have 202 ampere from here. Our threshold start current is 202 ampere, which is equivalent to 1.35 per unit. So how it was derived, this 1.35 unit, just multiply 202 ampere by 1 over the CT ratio. So we have this 200 by 1 multiplied by 1 over 150, that's why we have 1.35 per unit. Okay, on our time setting here will be a definite time set at 120% of the starting time for the nominal voltage. Okay, so to ensure that you we're going to avoid a nuisance tripping during the acceleration time of the motor. Okay, our acceleration time here or starting time is 3.6. Okay, so we add more 20%. Okay, that's why we multiply here by 120% times the starting time. So our setting for the starting time, our setting here for the time is 4.35 seconds. Okay, next, our thermal overload protection. So our first line of defense for the overload protection of the motor, or this is called relay 49. Okay, so from here we'll just multiply our threshold here, our setting we'll just multiply by 100%. Okay, this one on the rated current of the motor. Okay, that's why we have here around 102 ampere. Now you are asking why it's 100% of the rated of the motor. Because one it's normal in the industry practice when you're going to size the motor, it is only being sized around 75% to 90% of the driven load. So that's the reason why we are only providing here at 100% of the rated current of the motor. Okay, so our setting here is 100 is equivalent to 102 ampere or 0.6 per unit. So this one will just multiply the 102 ampere into 1 over the CT ratio. Okay, our curve will be based on IEC standard, okay, 60255, okay, part 8. Okay. Next, the relay 46 or the negative phase sequence protection. Okay, so we have here two threshold. Okay, the first threshold here will be an alarm. Okay, and the second threshold here will be for tripping purposes. Okay, so for the first threshold, we'll just multiply the rated current of the motor by 10%. So that's why here we have here around 10.2 amperes or 0.6 or 0.068 per unit. So how this is being derived? Okay, we'll just multiply, okay, the 10.2 by 1 over the CT ratio. Okay, our time setting will be definite time set at 5 seconds. Okay, next, our second threshold, our backup protection for the relay 46 will be, okay, 30% of the rated current of the motor. So we have here 30.3 ampere or 0.202 per unit. Okay, so we'll just multiply 30.3 times 1 over the CT ratio to derive this 0.202 per unit. Okay, with a definite time set at 3 seconds. For the relay 51 LR or the stall detection protection, okay, our threshold here, okay, is 200%, okay, of the nominal current. Our nominal current is 101. That's why we have here 202 ampere. So our threshold or our setting will be 1.35 per unit. So we'll just, okay, for this to arrive the 1.35 per unit, we'll just multiply the 202 by its by 1 over CT ratio. Then, our time setting will be a definite time set at 0.2 seconds. Okay? Next, the phase under voltage protection. Okay? So, this is always an standard uh, setting for under voltage, which is 80% of the rated voltage. So we have here the 80% for 11 kV. Okay, we have here 8,800 volts. So this 80% just multiply the bus voltage, which is the 11 kV. So we arrive here 8,800 volts, or our phase under voltage setting will be 0.8 per unit with a definite time set at 3 seconds. Our phase over voltage protection, or the relay 59, okay, we're going to multiply the rated voltage by 115%. So our setting will be 12,650 volts. Okay? Okay, just multiply 115% times the bus voltage, okay, to derive this 12,650 volts from here. So our phase over voltage protection will be 1.15 per unit with a definite time set at 1.5 seconds. Our phase time delay over current protection, okay, we have two criteria here. First, to, to calculate the setting or the threshold value, first, multiply the minimum short circuit current by 80%. The second criteria is we need to multiply the starting current by 155%. Whichever is lower, then that will be our set value. In this case, our set value, by the way, this 585.8 ampere is, we are multiplying only by 5.8 times the line current to 101. So that's why we have here the 585.8 ampere. Okay. So our set value here is 909 ampere. Okay. So in comparison to minimum, the 80% of the minimum line-to-line fault, we have here 7,283 ampere. But we cannot utilize this because we're not going to wait that the short circuit current will be go up to this high. So we are going to select a lower value, which is the 155% of the starting current. So we have here the 909 ampere or 6.06 per unit. To derive from this, we'll just multiply 909 ampere times each 1 over the CT ratio. Okay, so with our time setting here will be definite time set at 0.1 second. Okay. Next will be our relay 51G or ground time delay over current protection. Okay. Here, our threshold or our current setting value will just multiply the rating current of the motor 101 times the 5%. So that's why we have here 5.05 ampere or 5 ampere to rounding off. Okay? Or 0.2 per unit. So from here, we'll just multiply this 5 ampere by the 1 over the CT ratio. Here, since this is ground time delay overcurrent protection or relay 51G, we're going to use our zero sequence current transformer ratio, which is the 25:1 ampere. So that's why we have this 0.2 per unit value. Okay. So our time setting will be a definite time set at 0.1 seconds. Okay. By the way, this is our backup protection. This will be our second threshold protection. Second line of defense, okay, for the overcurrent protection, okay. Our first line of defense for overcurrent protection will be the relay 51. We have here the start number protection or relay 66. Okay? So our supervising time, okay, will be 60 minutes, okay? Maximum start number during supervising time 60 minutes or 1 hour. So meaning this one within 1 hour we are allowing only 3 number of starts. Okay? Innovation start time also 60 minutes, okay? Or equivalent to 1 hour. Okay? For this relay, we're going to disable the time between to start and the time for restarting. Okay? This will be okay. This is relay 37 or the loss of load protection. Okay. Our threshold setting from here will be 125% of the no load current of the motor. Our no load current is 26 amperes. So this will be multiplied only by 125%. We have here 32.5. So we'll just round off this one. Okay. So that's why we have here 33 ampere or 0.22 per unit. Okay. So we'll just multiply 33 ampere by the CT ratio to derive this 0.22 per unit setting. Our time setting will be definite time set at 1 second. Okay? We'll just want to ensure that this protection must be inhibited for the duration of the start. Okay? Our last protection, okay, this will be the Sonde temperature in windings. Okay? So, we have two thresholds here. One is for the alarm and the second threshold here is for the tripping of our contactor. Okay? So, our first threshold is set at 120 degrees centigrade. By the way, this is normally recommendation from the motor vendor with a definite time set at 0 seconds. Okay? Our second threshold, okay, if the high temperature still exists and reaches into 160 degrees, okay, this is the time that we will going to send signal on to open our contactor. Okay, so our time setting will be definite time set at 0 second as well. Okay, so our next topic we will be discussing on the relay setting calculation for a capacitor 11 kV capacitor feeder. Okay guys, thanks for watching.